d of beta Lm. What does it mean? This is jkth element of alpha representation, Lmth element of beta representation. This is an inner product in this fashion. This is what you get, sum over all the group elements G T jk of alpha into G star and d beta of Lm of G okay, and we define this 1 over G here is equal to, if alpha is different from beta, then they are not equivalent, they are two inequivalent representations, then this is equal to 0. So, first will be delta alpha beta. Second, if J is equal to L, J also has to be equal to L and K also has to be equal to L. Delta alpha beta, delta JL, delta Km. That condition comes because of this, its identity here. Okay, identity means if TS has to be identity if they are equivalent representations. You can always through some similarity transform bring it to that form. Okay, so we can assume that they are equal, because every representation is equivalent to a unitary representation. So, if two are equivalent in terms of UIRs, they are equal. Okay. Now, statement of this is called great orthogonality theorem. So, great orthogonality theorem essentially tells you that if you have two irreducible representations and you, so what actually this means, the following. Let me just illustrate it, which has elements E, C3, C32, sigma 1, sigma 2 and sigma 3. Okay, and we can write down, we have written down yesterday a representation. What is the representation? Two dimensional representation we have written down, 0 1, C3 is minus half minus root 3 by 2 minus root 3 by 2 minus half, and C32 is minus half root 3 by 2 minus root 3 by 2 minus half. Sigma 1 is equal to 1 0 0 minus 1, and sigma 2 is a product of these two, which means I will have minus half minus root 3 by 2. Yeah, okay. Minus 1 0 0 1, which means I will have a half here and 3 by 2 here, and root 3 by 2 here, and minus half here. And sigma 3 is, I get from here, half minus root 3 by 2 minus root 3 by 2 minus half. Is that correct? Are the just check whether these two are correct. So if I choose this representation, this is a two-dimensional representation. That means alpha is equal to beta here. Okay, I am only talking about a representation. Now I can form vectors. Okay, how many vectors I can form with this matrix? Elements, 4 vectors I can form. So first vector, I will call this as, let's say, V1. What are the elements of this vector? 1 1 element of this, 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 and 1 1 element of this. This is a vector. So with 1 1 element of every group, every representation matrix, I am forming a vector. Now let me take another vector with 1 2 element, 0 minus root 3 by 2, root 3 by 2. Of course, you should do it in the same order, okay, otherwise it will be difficult to show what I wanted to show. Root 3 by 2 minus root 3 by 2. Then V3, 2 1 element, 0 root 3 by 2 minus root 3 by 2, 0 root 3 by 2 minus root 3 by 2. And V4 is 2 2 element, 1 minus half minus half, 1 minus half minus half. So I have managed to write 4 vectors here. Okay, this is one representation. That means what? In this case, alpha is equal to beta, because everything is only one representation here. But what this orthogonality tells you is that these vectors are orthogonal to each other. This orthogonality tells you that this is orthogonal to this is orthogonal to this. Vectors are among themselves orthogonal to each other. These vectors will belong to a 6-dimensional vector space, that is this space. Okay. Now they are orthogonal to each other. If they belong to a given representation, then the vectors constituting of an element of 1 1 1 1 1 1 1 1 will be orthogonal to 1 2 element vector, 1 3 element 2 1 element vector, 2 2 element vector. But if you take this vector with itself, that means if you dot this vector with itself, then what will you get? You will get 1 plus 1 by 4 plus 1 by 4 plus 1 1 by 4 1 by 4. So you have 1 2 3 4, correct? What is V1 dot V1? One plus 1 by 4 plus 1 by 4 plus 1. We have 6. This is half. This is 3, right? What about V2? 3 by 4, 3 by 4, 3 by 4, 3 by 4. It is also 3. This is also 3. Okay, this is also 3. So now what you are getting here, this is 3, okay, but then when you are doing this dot product, there is see alpha is, if this is representation, djk is, if I put j equal to 1, k equal to 1, it is this element djk of E. d11 of E is this, d11 of C3 is this, d11 of C32 is this, okay, like that. So this vector I have made with d11 of G, where G is E, C3, C32, like that. This I have made with d12 of G, this I have made with d21 of G, this I have made with d22 of G. Now you can see that unless Jk is same as Lm, this is orthogonal. So let me not write this at this moment. So what you are getting here is 3. What is 3? We are getting each one, when I take dot product, is 3, right? So it is normalization, but that 3 is equal to the order of the group divided by the dimension of the vector space, or dimension of this representation on which this is defined. So dimension, this is a 2-dimensional representation. So 6 by 2 is 3.
How does it appear now that the relation, the dimension of
Okay. So there is something that I have left here. One can show that this lambda s is equal to trace of this s divided by dimension of V. The multiple of identity I left it here. Okay, this lambda s can be shown as trace of s divided by dimension of V. From this, because there is an s that is sitting here. Okay, so when I get this, this will go away and the dimension of V will remain. Okay, so if there is time, I will try to show this. But there are other representations also. Okay, so this is only one representation for this group. Final result is what is called great orthogonality theorem. That is, sum over all group elements, jkth element of alphath representation corresponding to an element G of G star into lmth element of beta irreducible representation of the same group element G is equal to order of the group divided by dimension of, I can call it as dimension of d alpha into delta alpha beta. If the two groups are inequivalent, then this is 0. Delta JL, there should be of the same row index, and delta Km, they should be of the same column index. So this is the only result that you have to remember if you have to use group theory for some applications. D alpha is the alpha irreducible representation. What is the dimension of that representation? That is dimension of the vector space on which that representation is in terms of d of beta also, because if alpha is not equal to beta, anyway it's 0. We can define character of a representation. So if you have d alpha, then character of this representation alpha corresponding to an element G is defined as trace of this representation matrix corresponding to G. which implies this is equal to sum over k d alpha of g dkk of alpha of g. So, whatever representation matrix you have, we will take the trace. Trace is sum of the diagonal elements. So, this is defined as the character. Now, notice that this character of a representation is, if you take A G A inverse, it is same as G G, correct? But this may be a different element. So, character is actually a class function. All those elements which are in the same conjugacy class will have same character, because elements in the conjugacy class are related by this conjugate operation, and trace is independent of this conjugate operation. So, chi alpha are class functions. Chi alpha are class functions. What does it mean? It means that they are same for all elements in the class. Now, you can see that we can have what is called character orthogonality. Character orthogonality, which is given by sum over G, or if you write down the character vectors chi alpha comma chi beta, chi alpha comma chi beta is equal to delta alpha beta, because there are no matrices, these are scalars. Okay, there are no matrix elements. So, chi alpha chi beta is equal to, if alpha and beta are two irreducible representations, then chi alpha chi beta is equal to delta alpha beta. In some sense, the character strings form a unit vectors for the vector space. You can also write, this is essentially what this is equal to, sum over G chi alpha of G into chi beta chi alpha of G star into chi beta of G is equal to delta alpha beta. But you know that instead of summing over all G, if I sum over only classes, then what happens? There will be terms of the same type for the class. So, we can write down this as sum over classes n alpha, that is the number of elements in that conjugacy class, into chi alpha of that class C star into chi beta of that class C is equal to delta alpha beta. Now, we can draw a very important conclusion from here. Number of irreducible representations is equal to number of classes. Number of how many irreducible representations will be there for a given group? They are equal to number of classes, because within the class elements are anyway related by a conjugacy operation. So, irreducible representations is equal to number of classes. So, for this group we have how many number of classes for C3V? For C3V we had one class E, other class C3, C32 and sigma 1, sigma 2, sigma 3. We have enlisted the classes yesterday. So, for C3V we have 3 classes. So, number of irreducible representations for this group is equal to 3. Okay. Now, what are their dimensions? That is our next question. Okay, we have 3 irreducible representations, but what are their dimensions? Now, that we will get the orthogonality relation tells you that you have a set of orthogonal vectors which are you have, like I wrote V1, V2, V3, V4. Okay, that is, all those 4 vectors will correspond to one irreducible representation, but here I know that there are 3 irreducible representations. That means there are totally 3 irreducible